Okay, so we have proved up to now that if rho epsilon greater than 0 is a family of mollifiers, and then f Rn to R continuous, then rho epsilon star f converges to f pointwise. And if f is continuous with compact support, then rho epsilon star f converges to f uniformly. Finally, we also saw that f is continuous with compact support, then rho epsilon star f converges to f in LP of Rn, 1 less than equal to p less than equal to infinity. Okay, we will now use this to prove some density theorems. So, the first theorem, D of Rn is dense in LP of Rn 1 less than equal to p less than infinity. So, proof. So, first step, so let S be the set of all simple functions on our phi on Rn such that the set of all x in Rn phi x not equal to 0, the Lebesgue measure of the set, modulus defines the Lebesgue measure for a set, is finite. So, the function vanishes outside a set of finite measures. So, then phi in S, if and only if, so phi in S implies automatically phi belongs to LP of Rn, because after all, what is the p integral of mod phi power p? It is nothing but sigma mod alpha I, measure of ai, where alpha ai is a set where the value alpha I is taken. So, if alpha is not 0, all these sets are finite measures, so they add up to this. Conversely, also phi simple phi in LP of Rn implies phi is in S, because it cannot be non-zero on a set of infinite measures being a simple function, because then the p integral will blow up. Okay, so this we have this. Now let f be greater or equal to 0, f in LP of Rn. Now any non-negative measurable function, you can approximate it by an increasing sequence of simple functions. So, phi n greater or equal to 0, phi n simple. So, phi n is less than or equal to f, there is no need for modulus because everything is non-negative, and f belongs to LP. So, this implies phi n is LP of Rn, implies phi n belongs to S, as we have just observed. Okay. Further, mod of phi n minus f power p, mod phi n minus f is less than or equal to 2 times f, so that is equal to 2 mod f power p, and this is integrable. And mod phi n minus f goes to 0 pointwise. Therefore, by the dominated convergence theorem, phi n minus f in LP goes to 0. Therefore, this phi n which increases to f also approximates f in LP, and they are all in S. Now, if f belongs to LP of Rn, arbitrary function, then you write f equals f plus minus f minus, then there exists phi n psi n in S. So, phi n goes to f plus, psi n goes to f minus in LPRN, and therefore this implies that phi n minus psi n goes to f in LP of Rn, and of course phi n minus psi n belongs to S. So, conclusion, S is dense in LP of Rn. Now, step 2. Okay. So, let phi belong to S. Then we quote a theorem, Lusin's theorem from measure theory. So, what does this theorem imply? There exists a continuous function G with compact support such that 1, measure of set of all x such that phi x is not equal to gx can be made less than epsilon. So, epsilon greater 0 arbitrary. So, for every epsilon we can find such a g, and secondly, norm of phi g in L infinity is less than or equal to norm of phi in L infinity. So, this, once you have this, it automatically means that norm of g minus phi in LP, what is this less than or equal to? After all, you have to take the integral only where the functions are different, everywhere else this difference is 0, and that is of measure less than epsilon, and the function itself is less than 2 times norm of phi. Therefore, you get 2 times norm phi in L infinity epsilon power 1 by p, and therefore this goes to 0. So, this implies that continuous functions with compact support dense in S with LP norm, and hence since S itself by step 1 is dense in LP of Rn, you have, and hence in LP of Rn. Remark, this is true for any omega contained in Rn O. So, in any continuous functions with compact support in omega, so denoted Cc of omega, is dense in LP of omega 1 less than or equal to p less than infinity, because we are taking integrals, we are not taking L infinity now. Okay. So, then step 3. So, f is can be approximated. So, f in LP of Rn, then for every eta positive there exists C G in Cc of Rn, norm f minus g in LP is less than eta. Then we know that rho epsilon star g converges to g in LP of Rn, we have already proved that, and therefore there exists for epsilon less than or equal to some epsilon naught, norm of rho epsilon g minus g in LP is less than eta, let us say eta by 2, both of these, and this implies that norm of rho epsilon star g minus f is less than eta for all epsilon less than or equal to epsilon naught, and rho epsilon star g, remember it is a convolution of a C infinity function and with compact support with a continuous function with compact support, and therefore the function is C infinity and has compact support as well, and therefore this proves the theorem completely. Okay. So, D of Rn is dense in LP of Rn. Okay, corollary. So, let rho epsilon epsilon greater than 0 family of mollifiers and let F belong to LP of Rn. Then rho epsilon star F converges to F in LP of Rn. So, every continuous function can be approximated in the LP norm by a C infinity function now, because F is locally integrable being a LP function, rho epsilon is C infinity with compact support, that does not matter. So, the rho epsilon star F is C infinity and it approximates F in the LP norm, and this is true for all 1 less than or equal to P less than infinity. So, proof. So, you take F in LP of Rn and let eta be greater than 0, fixed quantity. So, then there exists a G in CC of Rn, continuous function with compact support, such that norm F minus G in LP is less than eta by 2, because that is the first two steps of that theorem. Namely, we saw that continuous functions with compact support was dense, and then of course we concluded it for C infinity functions with compact support. Now, since G is in CC of Rn, so for all epsilon less than or equal to some epsilon naught, you will have norm of rho epsilon star G minus G in LP is less than, say, eta. So, let me take with a little foresight, let me write eta by 3. So, this also eta by 3. So, norm of rho epsilon star F minus F in LP is less than or equal to norm of rho epsilon star F minus rho epsilon star G in LP by triangle inequality. This is rho epsilon star G minus G in LP and then plus norm of G minus F in LP. Okay. So, now this is less than eta by 3, this is also less than eta by 3, and this equal to norm of rho epsilon star F minus G in LP, and by Young's inequality this is less than or equal to norm rho epsilon 1 norm F minus G in LP. Now, rho epsilon 1 is the integral of rho epsilon, is always unity, and this is less than epsilon by 3, and therefore, we have that for all epsilon less than or equal to epsilon naught, rho epsilon star F minus F in LP is less than eta, where eta is any arbitrary positive constant and therefore arbitrarily small, and therefore you have we have proved this corollary. Okay, so now theorem. So 1 less than or equal to P less than infinity, omega in Rn any open set, then d omega is dense in LP. So, if you remember, we used this fact when we are proving that for a locally integrable function, if you have integral f phi equal to 0 for all phi in d omega, then phi is identically 0. In proving that theorem, we assumed the first step was we said omega, it is integrable in omega and omega has finite measure, and there we used the fact that d omega is dense in LP, and therefore which we said we will prove later. So, we are redeeming our promise now. So, we are proving this theorem in this case. So, proof. So, as in previous theorem, CC of omega, continuous functions with compact support, is dense in LP of omega. So, this I have already made that remark. So, we already have this result. Okay. So, given eta positive, arbitrarily small positive quantity, and f in LP of omega, there exists a g in Cc of omega such that norm of f minus g in LP of omega is less than epsilon eta by 2. Now G is continuous with compact support contained in omega. Okay, support of G equal to K compact, and K is contained in omega. Okay, so you have omega here and you have a compact set K which is contained in it, which is compact. So if you take G tilde extension by 0 outside omega, extension of G by 0 outside omega, then you have the G tilde belongs to Cc of Rn. And what is G tilde? Support of G tilde is the same as support of G, which is K, okay, which is contained in omega. Now rho epsilon star G tilde converges to G tilde in LP of Rn, and this belongs to D of Rn. Because it is a C infinity function and its support is contained in support of rho epsilon. Now support of rho epsilon star G tilde is contained in support of rho epsilon plus support of G tilde, which is contained in B0 epsilon, the ball center origin radius epsilon closed ball, plus K. And if epsilon, and that will be still contained in omega because you are going to take a epsilon distance from K, so that will be still contained in omega for epsilon sufficiently small. So you have that rho epsilon star G tilde restricted to omega belongs to actually D of omega, because it is a C infinity function and the support is contained in omega, and since rho epsilon star G tilde converges to G tilde in Rn, so norm of rho epsilon star G tilde restricted to omega minus G in Rn, LP of Rn, in LP of omega, this is the same as norm of rho epsilon star G tilde minus G tilde in LP of Rn, and we know that this goes to 0, okay, because everything is 0 outside, and so this goes to 0, and therefore you have shown that therefore for epsilon sufficiently small, you have norm of rho epsilon star G tilde restricted to omega minus G in LP is less than eta by 2, and therefore this implies for epsilon less than or equal to epsilon naught, norm of rho epsilon star G tilde restricted to omega minus f is less than eta in LP, okay, and that proves the theorem. Okay. Then one more very useful theorem, 1 less than or equal to p less than infinity, f belongs to LP of Rn. Then you define tau h of f of x is f of x minus h, where h is a vector, fixed vector in Rn. Okay, so this is for all x in Rn. Now this you do not do in omega because x minus h may fail to be in omega, okay. So that is why we need all the elbow room we have, and therefore we have to do it in Rn, okay. Then limit h tending to 0 of norm f minus tau h of f in LP equal to 0. So proof. So Lebesgue measure is translation invariant. So this implies that tau h of f is also in LP of Rn, and in fact it has the same norm of tau hf in LP is the same as norm f in LP. That is just a translation invariance of the Lebesgue measure. And now let epsilon be greater to 0, small positive quantity, then there exists phi in d of Rn such that norm of f minus phi in LP is less than epsilon by 3. Now let us support a phi be contained in some minus AA power n. So it is a big box in which we are putting it. Then phi is uniformly continuous, and therefore there exists a 0 less than delta, which we can assume to be less than 1 because you can take it as small as you like, such that mod h less than delta implies mod phi of x minus h minus phi x is as small as we please, and I am going to put it as less than epsilon by 3 times 2 into a plus 1 power minus n by p. So then if you compute tau h phi minus phi power p integral over Rn dx, this is equal to, we just have to take the integral because h is less than 1, and therefore this will be over the integral minus a plus 1 power n, that will contain all the supports, phi of x minus h minus phi of x power p dx, and that you will get less than epsilon by 3 power p because of the choice of this when you have mod h is less than delta. So this implies if mod h is less than delta, we have norm tau h phi minus phi is less than in LP is less than epsilon by 3. Now what about norm tau h of phi minus tau h of f? This is nothing but norm of tau h of phi minus f, and that is equal to norm of phi minus f in LP, and that is of course less than epsilon by 3. So norm of tau h of f minus f is less than equal to norm of in LP tau h of f minus tau h of phi plus norm of in LP tau h of phi minus phi in LP plus norm of phi minus f in LP, and every one is less than epsilon by 3, and therefore you get that is less than equal to epsilon for all mod h less than delta, and therefore you have proved this particular theorem. So if you translate, then by small quantities it is continuous in LP. Okay, so we will, our next thing is to extend the notion of convolution to that of distributions, which we will do next.